numerical algorithms, because math problems don't always have neat solutions. Today, we'll explore root finding, interpolation, and numerical integration, and hopefully not lose our minds.
Hi everyone, welcome back. After learning algorithms and problem solving, we now turn the mathematics behind computing. Computers don't count in decimals like us, they count in binary. Today we'll learn number systems, binary arithmetic, and the basics of counting theory. In decimal, digits range from 0 to 9. In binary, it ranges only from 0 or 1. Octal uses numbers between 0 to 7.
Octal 0 to 7.
Hexadecimal uses numbers between 0 to 9 plus A to F.
Hexadecimal 0 to 9 plus A to F.
These systems are just different ways to represent the same quantity.
In decimal, digits range from 0 to 9. In binary, only 0 and 1. Octal uses 0 to 7 and hexadecimal uses 0 to 9 plus A to F. These systems are just different ways to represent the same quantity. It's like having different flavors of ice cream, but the ice cream is still the same.
So for example, 245 in decimal would equate to F5 in hexadecimal. Let's move on to the next topic called conversions. To convert decimal to binary, divide by 2 until you reach 0. Then read remainders from bottom to top. For binary to decimal, multiply digits by powers of 2. I would encourage you guys to pause here and write each step for yourself.
To convert decimal to binary, divide by 2 until you reach 0. Then read remainders from bottom to top. It's like following a recipe, but the recipe is math.
For example, in binary to decimal, we basically multiply by the power of 2 to convert it into a decimal single digit number. For example, 1 into 2 to the power 4 plus 0 into 2 to the power 3. This is because decimal counts values from 0, 1, 2, 3, 4, which are the powers here. So these are the powers which get multiplied. So the powers of 2 are multiplied to each binary value to get the final decimal value. And for decimal to binary, what we do is we just keep dividing this number by 2 repeatedly until we get the remainder. So in each value, we get a remainder, and that remainder becomes a binary value. Try it for yourselves. So let's move on to the next topic now. Binary arithmetic works just like decimals, but with simpler rules. Carrying happens at 2 instead of 10. For example, you can see here that 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 1 becomes 10 because we carry 1. Similarly, if we want to add two binary numbers, 1011, which is 11 in decimal, and 1101, which is 13 in decimal. So how would we do that? We use the similar logic that we had here to get the answer, which is 11000, and in decimal it is 24. You can try it for yourselves. Let's move on to the next topic now.
Binary arithmetic works just like decimal, but with simpler rules. Carrying happens at 2 instead of 10. It's like playing a game, but the rules are simple. Counting tells us how many possible arrangements or selections exist. With permutations, order matters. With combinations, order doesn't matter. It's like choosing your own outfit or your friends. So now we move on to the next topic, which is basically called theory of counting. Pause here, solve these problems, and compare with my solutions in the notes. Don't worry if you get stuck. It's all part of the learning process. Today, we build the foundation, number systems, binary math, and basic counting. Next, we'll see how this leads to graphs and algorithms. Stay tuned, it's going to be fun. It's like having different flavors of ice cream, but the ice cream is still the same. Although, if you're stuck with binary ice cream, it's just 0 and 1 flavors. By the way, have you ever tried counting sheep in binary? Don't worry, we won't make your count to infinity. Or will we?
Counting tells us how many possible arrangements or selections exist. With permutations, order matters. With combinations, order doesn't matter. Let's take a look at this example. So in theory of counting, we have firstly the rule of product. So what does this state? So for example, we have three shirts, right? So let's say this is a shirt. This is, let's say, a shirt, and then we have a pant, right? And let's say we have similarly, so let's say this is one. We have another shirt, and we have, so basically we have three shirts. And let's say we have one pant, and similarly we have three pants, right? So what does the theory of counting state? What it does is basically we have to count the number of outfits that we can make from this. So to do this, what we do is basically we pair each shirt with each pants. For example, this shirt goes with first pant, second pant, and third pant. Similarly, second shirt goes with first pant, second pant, and third pant. And third shirt goes with similarly first pant, second pant, and third pant. So this is how we get all the possible permutations of all the possible combinations of these shirt and pant, right? A simple way to do this is by multiplying simply. So for example, three shirts into two pants is equal to six outfits. That is what we get. If you add this all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So you will get the similar thing. Basically for three shirts, right now, what happened was here we took, instead of two, we took three pants. If we change this to two, for example, let's say I say that there is only two pants. So now if you see 1, 2, 3, 4, 5, and 6. So total of 6 outfits, as we could just do it by the rule of product. Now, how do we represent this mathematically, right? So to represent this mathematically, we say NPR is equal to n factorial upon n minus r factorial, right? Here, n is basically the number of shirts, and r is basically the number of pants. So what we do is we say 3 factorial divided by 3 minus 2 factorial, which is 1 factorial, right? Now 3 factorial we can write as 3 into 2, right? 3 into 2 into 1. And 3 minus 2 factorial is basically 1 factorial, which is 1. So here our answer is 6 again. I hope this is clear. N basically represents the number of uh, commodities that we have, and R is basically the number of choices that we have to make from that. So P is basically what we call as permutation, right? So that is what we are doing. We are basically counting the number of permutations. Permutation means counting. Patience is basically counting. N is equal to 3 here. R is equal to 2 here. I hope this is clear. Okay, moving on. Before this, with permutations, orders matter. With permutations, order matters. With combinations, order don't matter. Order doesn't matter. For example, how many 3-digit numbers can be from 1, 2, 3, and 4? Try it out. So let's say we have 1, 2, 3, and 4, right? How many 3-digit numbers can be formed from this without repetition? Pause here.
Binary arithmetic works just like decimal, but with simpler rules. Although if you're not careful, you might end up with binary mess.
So the answer is 4p3, which is equal to 24. You can try this out. Let's move on to the next topic.
Counting tells us how many possible arrangements or selections exist. With permutations, order matters. With combinations, order doesn't matter. Although if you're counting permutations, you might end up with a wardrobe full of outfits. And if you get really stuck, you can always ask your friendly neighborhood math superhero. Stay tuned, it's going to be fun. Although if you're stuck with binary ice cream, it's just 0 and 1 flavors. You might get a brain freeze from all the ones and zeros. And if you mess up, you might end up with a binary cake that's all 0 and 1s. And don't worry, it's not as hard as baking a cake, unless you are allergic to math. If you're not careful, you might end up with a
Pause
binary
here.
mess.
Solve these problems and compare with my solutions in the notes.
Although if you're counting permutations, you might end up with a wardrobe full of outfits. And if you're counting combinations, you might end up with a party full of friends. And if you can get really stuck, you can always ask your friendly superhero. Or you can just Google it. But where's the fun in that? Don't forget to practice your binary counting skills. Or you might end up counting sheep in decimal. But don't worry, it's not the end of the world, unless you're a math nerd. Then it's a tragedy. By the way, have you ever tried counting sheep in binary? It's like 1010101010 sheep. So to recap and close, we'll discuss a few pointers here. Maybe we'll discuss the secret to making binary arithmetic fun. Maybe we'll discover the secret to throwing the ultimate math party. And if you're counting combinations, you might end up with a party full of friends. Maybe we'll discuss the secret to making math fun again, for everyone.
Today, we built the foundation, number systems, binary math, and basic counting. Now, we'll see how this leads to graphs and algorithms.